Hello all, I am Rani. In this talk, I'm going to present our work, a multi-scale consensus method using factor analysis to extract modular regions in the functional brain network. Finding node communities in functional connectivity network enable us to understand which regions of the brain function together during specific scenarios. Example, resting state, a cognitive task, etc. Our motivation for this study is to determine those co-activated regions in the brain during resting state using exploratory factor analysis of an entire correlation matrix, that is, by not thresholding. However, there are issues with the EFA for the choice of number of factors NF. We can ideally use NF from the ground truth, but for this study we don't have one. So the question here is, how do we work with EFA for finding communities or clusters in a network? We propose to use a multi-scale approach for this. So instead of single scale, that is single NF value, now we use several scale values and then use consensus to consolidate our results. EFA with single value or scale suffers from factors replication, reliability, and generalizability of the process. A multi-scale method, that is exploring node partitioning of EFA with multiple number of factors, will overcome the limitations of single scale EFA. Hence, EFA is performed at multiple values and the node partitioning results of different scales are aggregated using a consensus method. We use these ensemble runs of EFA and a consensus of co-association matrices to compute an averaging of results of all combinations of ensemble. Before implementing EFA, the correlation matrix is checked for its positive definiteness to ensure non-singularity. EFA is an experimental method that uses intercorrelated variables to find factors. In factor analysis, each random variable is expressed as linear combination of the factors. Here, y1 to yn are nodes of the functional connectivity network, and f1 to ff are the factors. Always number of factors is less than nodes. Lambda are the factor loadings respective factors, and eta is a error term. Changing the number of factors f will give different node partitions on the same network. In this work, f is explored over the range of values and co-associations of the node groupings is measured. For creating a consensus matrix, we aggregate the node partitioning results and not the factors. And also the aggregation is done using a consensus matrix D. The elements of D are the probabilities of any two nodes coexisting in a community, aggregated across n experimental runs. Here n is the number of scales in the interval. The delta function in the equation is 1 if node I and j are in the same node partition P in kth run. Otherwise, delta function is 0. We perform low-end community detection on the network represented by D to find communities and measure modularity and Jacquard similarity values. As a case study, we have used the resting state fMRI data of Beijing Normal University from 1000 functional connectome project. The data set is of 198 healthy right-handed volunteers in the age group of 18 to 26 years. Functional network is generated for each subject using a 90-node AAL atlas. A pairwise PCC is computed between mean time courses of the nodes. The functional networks are aggregated across all subjects to give the final fully connected 90 cross 90 weighted and undirected network. Using NF as the scale and running an ensemble of experiments with different values of NF adds the exploratory and experimental characteristics of EFA. How do we find different values for NF for multiscale? By finding the salient values of the number of partitions pertaining to the case study from literature and then identifying an interval covering these values. The interval of scale is attained using multiple sources and experiments. First one, ground truth. The ground truth here is a node partitioning of the FCNs generated using the same fMRI data and using AIL Atlas with 90 nodes in the work uncovering intrinsic modular organization of spontaneous brain activity in humans. The number of communities found in the work are 5. Number 2 is RSNs, that is resting state networks found using PICA, which is similar to PCA. It is found as 5 RSNs. Number 3, we have done parallel analysis and scree test plot on the completely connected functional connectivity network and found NF as 9. We also explored the traditional studies, that is edge prone networks. So for that we have identified edge cutoff value as 0.5 using percolation analysis. Number 5, using Low-Bain community detection on the sparsified network, we found 7 communities. And finally, with the info map on a sparsified network, we found 12 communities. Hence, the interval of number of factors for EFA is 5 to 12. We have explored different node partitions of the same FCN by varying NF from the chosen interval for finding patterns. Here we have measured and depicted the modularity and Jacquard similarity values for an ensemble of runs of EFA. Modularity values at lower triangle and Jacquard similarity values at upper triangle, a single scale EFA modularity values are shown across the diagonal. Using this result, we can study how would different subintervals of the chosen interval perform in terms of Q and SJ, that is Jacquard similarity. Jacquard similarity is compared only when number of partitions of D is equal to ground truth clusters, that is 5 clusters. We observe that several of the runs yield number of partitions equal to 5 numbers in this upper left triangle. Our results show that the presence of 5 factors in the subinterval used for multiscale analysis improves the Q and SJ scores. Maximizing Q gives the optimal subinterval of scales to be 5, 6 for multiscale experiments and 5 for single scale experiments. We thus find high values of Q and SJ co-occurring for the entire interval 5, 12. Overall, we conclude that the optimal number of partitions is 5 for this dataset. We compare our results against a state-of-the-art consensus method, namely the hierarchical consensus method. Both modularity and Jacquard similarities are great with multiscale approach, and the same is revealed by visual inspection of node groupings using Sankey plot. Lesser edge crossings from multiscale partition is observed when compared with hierarchical consensus clustering. Thus, the node partitioning of EFA multiscale has a higher relative likeliness to the ground truth than that of HC for this dataset. Single-scale EFA interestingly showed hierarchical modular organizational behavior with increase in NF in this dataset. Since there is no unique hierarchical grouping in FCN at resting state, this result is not generalizable. With the Sankey plot, we notice that the hierarchical behavior of node groupings from 5 clusters to 7 and then 9. The spatial layout of the nodes on brain surface of our optimal node partitioning from multiscale consensus method demonstrate hemispheric symmetry. We have used BrainNet VR tool to visualize the same. Most of the nodes of the modules module 1 is belonging to the motor and auditory regions, module 2 default network regions, module 3 limbic and subcortical areas, module 4 visual processing regions, and module 5 predominantly with the nodes of attention processing regions, including frontoparietal cortices. We conclude that EFA can be used for extracting functional segregation of the human brain using a multiscale approach facilitated by a consensus method. We have implemented EFA with varying intervals of NF, thus giving an ensemble of experiments. We have determined the optimal interval of factors which gives high Q and high Jacquard similarity values and is comparable to the state-of-the-art methods. The limitation of our method is in identifying an appropriate interval for NF for multiscale method. The overdependence of multiscale EFA on the empirical values of NF affects the results. For example, in this data set, if NF value of 5 and 6 are absent, we will not be able to observe the hierarchical behavior. Thank you for your attention.